Hi, and thank you very much to all the organizers for the invitation. So I will talk about isospin breaking corrections to QCD observables. The talk will be a bit more topical than QCD observables, but I will try to make also a bit of an overview at the end. So I will. So people were right. Okay. Okay. So the talk will follow these. So I will start by addressing the reasons why isospin breaking corrections are relevant in some phenomenological and lattice also calculations. I will describe why, how these effects can be included in lattice calculations, and then I will describe what can we do on the lattice. So what are the observables that we can compute? So the motivations are, there are several motivations. Here it's just an example, and it's related to indirect searches of new physics in the in flavor physics. And we know that we can do it, for example, by so the pointer, I think it's this one. No? Oh, okay. Yeah, sorry. Okay. We can do it by measuring as precisely as possible the elements of the CKM matrix that describe the mixing of quark flavors under weak interactions, and we test all the unitarity constraints that have to be respected in the standard model. A failure of this test could be a hint of new physics effects. These elements can be extracted, for example, from the study of leptonic and semi-leptonic decays, and we see that the decay rates that can be measured experimentally can be expressed in terms of the CKM matrix elements and some quantity that contains all the non-perturbative effects of the strong interactions. These quantities can be computed on the lattice and can be computed also with a very good precision. And here I show the averages reported in the flag review. And we see that the level of precision is below the percent, which means that at this level, effects due to QED and strong isospin breaking cannot be neglected in the calculations. I also want to stress that the importance of obtaining precise results for VUS or VUD in this case is also made stronger by the current tensions that there are in the first row unitarity tests. And as you can see from this picture, that I have to say it includes QED corrections from the Rome-Southampton collaboration. You can see that there are tensions that go from 1.7 to 5.6 sigma, depending on which quantity one takes into account. Of course, these are tensions that could evolve in time, and I would be careful in taking them to serious, well, not seriously, but they might change because they're really sensitive to systematic uncertainty, and in particular on isospin breaking correction also. So on our side, what we can do is to try our best to improve our theoretical estimate of these matrix elements and compare to experiments. Other motivations, if this was is not enough, come from other calculations. We heard the effort from the lattice community on computing the HVB contribution, well, the mu G minus 2, and eventually isospin breaking corrections will play a role if the target precision is at the level of the per mil. And also, there's some improvement in the calculation of CP violation parameters, like epsilon prime over epsilon in K2 pi pi. And as these results will reduce its uncertainty, then also their QED effects might become relevant. So I will focus on mainly weak decays. And in this context, what we have to do is to add, as I said, QED and strong isospin breaking effects. These effects are related to the inclusion of electromagnetism and the inclusion of and the treatment of the up and down quark masses, not as they generate quarks, but with different mass, which is a feature that is present also just in QCD without the inclusion of electromagnetic corrections. These are corrections of order 1%, and the quantities I've shown before then get some correction that I call here delta R. At the moment, these corrections are taken from KPT, but there's nothing that prevents us to compute them on the lattice, and I will show you how we have done it for leptonic decays, at least. The difficulty, there are many difficulties in including QED, especially QED corrections on a lattice with a finite volume. First of all, QED is a long-range interaction, and long-range interactions don't really like to be confined in a finite volume with periodic boundary conditions. And as a consequence of trying to define it in a finite volume, one will also have some potentially sizable finite volume effects that don't scale exponentially, like as we increase the volume, like in QCD, but can be power-like. Then also, when studying decays, one has to face also the appearance of infrared divergences in the intermediate steps of the calculation. And then there's something that has also to taken into account, which is that QCD plus QED and isosymmetric QCD are two different theories that require different renormalization procedure and a different scale setting. We can understand the difficulty of including QED corrections in a finite volume with periodic boundary conditions by looking at the Gauss law. So from the Gauss law, we see that by imposing periodic boundary conditions, basically only states that have a total zero charge can be studied. And this poses an issue if we want to study, for example, decays of charged particles or corrections to masses of charged particles. So in the years, there have been many proposals to solve the issue, and these results in defining in many different ways QED on the lattice. Here I show just the formulations that are being used at the moment. We have QEDL, which is a prescription that solves this issue by removing the spatial zero mode from the photon spectrum. And it's a non-local constraint that generates some 1 over L cube corrections in our finite volume calculations. Then there is QDM, which consists in adding a mass to the photon. Then we have QED C star that solves the issue by redefining the boundary conditions and using C star boundary conditions. And Then we have a more recent proposal that is called infinite volume reconstruction, and I will mention something later, and it basically consists in treating the long-range part of the QCD correlators in a special way, such that QED can always be defined in the infinite volume. So I will mainly focus, though, on QEDL, which is the formulation that has been used in the two calculations that are currently have currently been done for electronic decays. So what can we do? We can do really many things, and most of the things I put in this list have someone that started, that worked on that or started working on that. So we can compute corrections to hadron masses, and so, for example, determine separately the masses of the up and down quark mass, on the up and down quarks. Then there's lots of work including these corrections in the HVP contribution to mu and G minus 2. Then we can study leptonic and semi-leptonic decay rates. And something that recently people are interested in is to compute corrections to the epsilon prime over epsilon in K2 pi pi. In all these contexts, we need these kind of corrections as the QCD, as the hadronic uncertainties decrease. So in all these cases, there's been improvement in the recent years on the QCD side, and so these corrections become relevant. I have to say that it's also a growing field, so I expect that some interesting stuff will appear in the near future. As I said, Okay, I will focus mainly on isospin breaking corrections to leptonic decay rates. There are two calculations. The first one from 2019 by the Rome 123 and Southampton collaboration that used QEDL as a regularization of the QED action on the lattice. And then a more recent one from 2022 from the RBC UK QCD collaboration. And then there's a recent proposal with QED infinity, but there's no complete lattice calculation on that yet. Here I just show all the things I will not be able to go through, and I will put some references in the in the backup slides for people interested in reading about it more. But there is some work in any of these topics. So these are the two calculations at the moment in the literature on leptonic, on isospin breaking corrections to leptonic decays, and I had the privilege of being part of both. In the first one, during my PhD in Rome, we used twisted mass fermions to compute separately the corrections to the kaon and the pion decay rates, the pion and kaon decaying into muons. We used multiple volumes and lattice spacings, but using all unphysical pion masses. The more recent one, during the postdoc in Edinburgh, we computed the corrections to the ratio of kaon and pion decay rates using domain wall fermions. We used physical quark masses, but only at the moment only at one lattice spacing and one volume. So as I said, one of the difficulties of including QED in the calculation of decay rates is how to treat infrared divergences that appear. We know that only the sum of the contribution from virtual corrections and the contribution from the emission of real photons is infrared finite, and a way to treat this in a lattice calculation has been proposed in 2015 by the Rome Southampton group, and basically consisted in adding and subtracting the same quantity, which is the decay rate computed in the point-like approximation. This exploits basically the universality, the so-called universality of infrared divergences, of QED infrared divergences, which means that these logarithmic divergences do not depend on the internal structure of the decaying hadron, but only on their mass and charges. And so in this way, we are able to work with separately infrared finite quantities. And the first two terms, which are the structure-dependent contribution from the virtual decay rate and the point-like decay rate, these are enough if we want to study the decays of kaons and pions into muons. And there has been some work on that, also on studying the finite volume scaling of this quantity. While these last terms, which are the structure-dependent contribution related to the emission of a hard photon, these are really necessary if you want to study decays of kaons and pions into electrons, or if you want to study decays of heavier mesons like D and B. There's been recently lots of work in computing these the form factors that enter this decay, and you can find them all in these references here. For the moment, I will focus on the first part, so on how to compute on the lattice the virtual corrections. And this is basically, well, it looks simple. It's actually a bit more involved, but one has just to compute three quantities. Some corrections to the matrix element, so to the bare decay amplitude. Some corrections to the meson mass of the decaying particle, and some correction also to the renormalization of the weak operator. So this step is really non-negligible because one has to take into account the matching of the lattice regularization to the weak, to the Fermi theory, basically. And there's been some work done in the 2019, and I presented at Lattice also in 2019. But this step can be avoided if one is interested just in the calculation of the corrections to the ratio of kaon and pion decay rates, because if one uses a mass-independent renormalization scheme, then this contribution cancels in this ratio. So we just have to compute the corrections to amplitudes and masses. This is something we can do, but it's a bit intricate in the sense that since we use the Rho 1, 2, 3 perturbative method that consists in expanding the full QCD plus QED path integral around these small parameters, isospin breaking parameters, then this results into a series of diagrams that we have to evaluate and analyze. Diagrams with photons exchange between the quarks, photons exchange between quarks and leptons, and also mass corrections to the quark lines. And also here you see, in principle, one should consider all kinds of disconnected diagrams that for the moment have not been included in both the Rome calculation and the RBC UK QCD1, in which we employed the so-called electroquenched approximation. This is quite a limitation, and we'll hear more later in, I guess, soon in the talk by Tim on how to move forward and go beyond this approximation. The two calculations had shown really a nice agreement also at the level of the behavior of the correlators. This is from the Rome-Southampton collaboration. This is the more recent one. And this is the behavior of the correlators with the photon exchange between quarks. This is the behavior of these other contributions. And we see also here a nice agreement in the behavior of the of the correlators between the two calculations. And this agreement also resulted into an agreement in the final result, at least in the current, within the current uncertainties. So here I report the three results currently available for these quantities for delta RK-pi, so for the ratio of kaon and pion decay rates, decaying into muons. Here is the chi-pt result, here's the Rome Southampton result, and here's the RBC UK QCD1. So first of all, I think it's really a nice, okay, it's a nice thing that we have a second calculation because it makes it, I think it's a strong evidence that these quantities can actually be computed on the, from lattice calculations. But the recent calculation also highlighted some problematic, some potential issues with finite volume effects that dominate the current systematic uncertainty. We know the scaling of this quantity. We know that it has inverse powers of L, and we know also how to estimate these, although the correction at order 1 over L cube, we know it only in the point-like approximation. And since in the point-like approximation this gives a quite sizable contribution, we decided to quote a large systematic uncertainty since we only have one volume. Of course, from this situation, we want to escape somehow from this situation that in which the error is dominated by these finite volume effects. And of course, the obvious way would be to repeat the calculation on multiple volumes and take an infinite volume limit. It's expensive, but we're working on that. One could also compute explicitly these missing terms in the expansion, but we are actually thinking on some other way, so a different way to formulate QED that removes these finite volume effects at order 1 over L cube. And this is something we are recently working on with the group in Edinburgh, and it basically consists in a redefinition of the QEDL action. Basically, in QEDL, as I told you, we remove the spatial zero mode, while the proposal we make here is not to remove it, but to spread it over the neighboring modes. In this way, what happens is basically that once we take the infinite volume limit, these redistributed modes on a given shell around the zero mode reproduce in the infinite volume the contribution of the zero mode. And this, in practice, consists in removing the term of order 1 over L cube. It's quite easy to prove it in systems with zero velocity, so this can be proved for hadron masses or for the HVP. So the errors can be pushed to 1 over L to the fourth. It's a bit less trivial, the proof for quantities that depend on a velocity. I will not go into the details of that, but we are testing this formulation, and there are more details in my plenary talk at Lattice 23. I just want to briefly mention that there's also some work ongoing that uses in which this collaboration with this group uses an orthogonal approach where QED is formulated in the infinite volume. And here, basically, the idea is to compute radiative corrections combining hadronic correlators computed on the lattice and some infinite volume QED kernels. There's still not a lattice calculation done, so we need to see what are the other systematic effects. But the advantage of this approach, as they claim, would be that the finite volume effects are only exponentially suppressed and no power-like corrections. Okay, so where are we for leptonic decay rates? We have, again, a current tension in the CKM unitarity that requires us to include isospin breaking corrections. This has been done by two different groups for the light meson leptonic decay rates, and these calculations have highlighted a crucial role of finite volume effects. So there's lots of work now in understanding how to tame these effects. Once this is solved, we have to move forward and move to some unquenched calculations, and we'll hear in a bit from Tim about it. And who knows, we might discover that some other techniques can be applied to these kind of works. I want to conclude by flashing all the things that I showed you before that I didn't have the time to talk about, but as you see, there's an intense work ongoing on the calculation of these corrections, and it might be probably also useful to put them somehow in a rough temporal order. At the moment, the collaborations are working intensely on computing these QED corrections to the HVP and to leptonic decays. But there's people also that started working on the applications to semi-leptonic decays and also to hadronic decays, to K2pi. These two presents many more complications, and but I think that we'll have in the future some nice, interesting results. So thank you.